All right, so the next thing we're going to look at is the storage of electrical energy on a capacitor. And the way energy is stored is positives and negatives are separated. So if we remember, we look at what our capacitor looks like. We end up with a bunch of positives on one side, negatives on the other side, and those are driven by some voltage difference. It can be a battery, a power source, whatever. But as they're separated, what we're doing is we're doing work. Energy is stored as work done on the capacitor. So that work is now energy stored in there that the capacitor can then do work later. This is so that your electric field can do work. Skipped ahead a little there, but there we go. So we look at work. Remember, work for an electric charge is just the charge across the voltage that it goes. So we're going to look at what voltage change it does. In that case, it's going to be the charge from whatever voltage it starts at to what it ends at. Well, the capacitor is not charged to start. So it's just going to be voltage final divided by 2. So what we get here, and if we use capital Q, this will start to look more familiar with what we know. Work is just equal to the change in electric potential energy, which is going to be equal to 1/2 QV. So this is the first way. Now we can start using the capacitance equation to substitute variables in here. So if we use Q equals CV, we can plug in for Q. What we're going to get is 1/2 CV squared. Just remember, because Q equals CV, we plug this guy in there. That's what we get. Now if we use, and we plug in for voltage, voltage is going to equal Q over C. So if we plug into this one, what we're going to get is 1/2 Q squared divided by capacitance. So now, based on that, I would like you guys to try out this problem over here. A camera flash has a capacitance of 660 microfarads and a potential difference across it of 300 volts. So I want you to take a second, pause the video, and try to solve for what is the energy stored on this capacitor. And then if I release all of that energy in 0.001 seconds, I want to know what the total power is. So take a second, pause the video, try it out. All right, in this case, I've got C and V, so I want to use one of these equations over here. 1/2 CV looks like it works for me. So UE equals 1/2 CV squared. There we go. So then I'll just plug my numbers in. 660 times 10 to the minus 6th. It's going to be 1/2 of it. And then 300 volts squared. And when I plug those numbers in, I get the energy of approximately 29.7 joules. Now, if I take that, and I'm going to remember that power is just energy over time. If power equals energy over time, then I'm going to take my 29.7 joules, divide it by 0.001 seconds. When I have that, I'm just multiplying by, let's see, that'd be 1,000. So I'm going to end up with 29,700 watts of power. All right, now, so I've got 2 plates, both have a charge Q, and they're separated by a distance D. If I separate the plates to 2D, so they were here, move them to here, I want to know what happens to the following variables. So go ahead, pause the video, just try and use the formulas we've got and figure out what you can. And then we'll go back through it and see if you guys understood it. So let's look at the equations here. Our capacitance equation is K epsilon naught A over D. If I increase D, what that's going to do is decrease my capacitance. Now, if my capacitance decreases, let's check here. With charge, we really have not moved the plates or allowed any, or we've moved the plates, but we haven't allowed the charges to go anywhere. So they're just separated. There's nowhere for the charges to flow. There's just 2 plates right now that have a charge Q. There's nowhere for the charges to go in and out, so Q is going to remain unchanged. Based on that, we know that electric potential energy, 1/2, let's see, 1/2, where's my equation for it? is Q squared over C. So if Q squared doesn't change, C goes down, that means my electric potential energy has to go up. I have a smaller thing in the denominator, which makes my product or my result a lot bigger. Now, based on this, since we know that, let me see here, Q equals CV, that means V equals Q over C. And this should make sense because our voltage should go up. So we come down here. Q is unchanged, C goes down, makes voltage bigger, and that makes sense because if our voltage is going up, then our electric potential energy should be going up as well. Because remember, electric potential is just how much energy a given charge would have crossing that, so that makes sense. Now, one last thing we're going to look at over here is relating our electric potential energy to our electric field. First thing I want to do, I want to look at voltage and capacitance because my electric potential energy has both of those in there. Now, if I make R and D both the same unit, I'll just choose D. If I put those in the same thing, I can now plug into here. So 1/2 CV squared. I get 1/2 K epsilon naught A over D times electric field times my, hold on, this D should be outside. There we go. Now we can cancel it just with one of the D's when we do it. One of these will cancel out with that, and we'll just be left with 1/2 epsilon AD over E squared. A times D, so this is the area of the plate, times how far apart they are. That's just giving me the volume in between the plates. So now if I take my electric potential energy and divide it by the volume, that's just the charge density in that area. That's going to be equal to epsilon naught times my electric field strength squared over 2. And that'll be it for this section of the notes.